Welcome to the very first open lecture hosted by the Simons Institute for the Theory of Computing. I'm Alistair Sinclair, the Associate Director of the Institute. Before I introduce today's speaker, since this is the first such lecture, let me just say a few words about the Simons Institute. So the Institute was established a year ago through a $60 million grant from the Simons Foundation. And its mission is to bring to the Berkeley campus research leaders on specific topics who come together for a semester and work together. The people we host range from graduate students all the way up to gray eminences. We typically run 2 programs per semester. So this semester we're running a program on real analysis in computer science, and a program on theoretical foundations of big data analysis. So these, we have around 90 visitors during the course of the semester, and we invite anybody on campus to come over to the Institute, which is housed in Calvin Lab, a circular building between the law school and the business school on the other side of campus. We have great interaction spaces and lots of smart people visiting us who are all on sabbatical and all have lots of time to talk to you and each other. So these open lectures, which we host 4 per semester, are designed to inform the rest of campus about the activities that are going on in the Institute. So we invite prominent visitors from the Institute to give a talk that is accessible to a broad scientific audience. Let me introduce today's speaker, Professor Nati Linial from the Hebrew University in Jerusalem. So Nati's been at the Hebrew University since prehistory. I think he did his PhD there, and he's for many years been a professor there. He did flirt with California briefly. He was a postdoc at UCLA a long time ago. Nati has very wide interests in combinatorics, in algorithms, in the application of geometric and analysis techniques to theoretical computer science, and also in bioinformatics. He's the author of around 150 research papers. He's a fellow of the American Math Society. He's also a great inspiration to young researchers. His PhD graduates have positions in many leading departments. Together with Jeff Kahn and Gil Kalai, Nati essentially invented the modern field of analysis of Boolean functions, which lies at the core of our current research program on real analysis at the Institute. And Nati's been a real force at the Institute already this semester. This is, I think, the 4th talk that he's been asked to give, and he's asked questions in all the other talks. And he's kept everybody generally on their toes in the building by going around and engaging in interesting conversations. So today, Nati's going to give a talk that actually spans both of our programs, both the big data program and the real analysis program. So he's going to tell us about the local... the title has changed slightly, but anyway, how to read large graphs.
Thank you, Alistair, for the very kind introduction. It's a subject that I'm really happy to be speaking about. I hope I found the middle way between being accessible to a wide scientific audience and still being of interest to people who work in the area. So my main goals are, to explain to you what the problem is, and it's really much more than a problem. I really think we have to develop a new kind of science to deal with this set of problems, so I'll try to explain what they are. By no means am I claiming that I know how to do this, but at this stage I think I can suggest a few viable and interesting directions of attacking these kind of problems and suggesting an approach to them. And in particular, there seems to be a major disconnect between people who use this or need really practical answers to these questions in the mathematical community that has some of the tools available. And one of my main hopes is to at least hint at the two camps about the existence of the other people and encourage collaboration. So this is a graph. We will see many more of those later on. Can anyone guess to what this is related? This is, right. Okay, so this is about cooking, Thanksgiving, and you can see here, I mean, honestly, I don't quite exactly understand how this was created. It's not so important. But basically, you can, whoever created this looked at all sorts of recipes, and edges connect the fact that you can replace crackers by croutons in some recipe. This is what these edges, but this is just to indicate to you that graphs, large graphs, are all over the place. I don't know if you're aware of this, but about a year ago, the European Union invested about 1.2 billion euro, which is about $1.6 billion. They're buying a graph for 1.6 billion. Well, I'm exaggerating a little bit. They actually, this is the BRAIN initiative, where one of the main goals is to create this huge graph, where vertices are neurons and edges denote synapses, connections, and so on. So really, a lot of what we want to understand and know in current and modern science and technology is encoded in terms of graphs. And about this, that we are very bad at looking at, as humans, we are very bad at looking at big graphs and understanding what's going on there. And therefore, we need some technology to address this thing. So this is the basic question. We have to deal with very big graphs, and what do we do with this? So let's come back to something that you all, or some of you, or many of you have seen in this way or another, even if you don't have a particularly advanced background in the mathematical sciences. What's the basic logic of statistics? We're bombarded by a large number of, a large collection of numbers, and we want to make sense of it, right? And these numbers come from somewhere, from some domain in which you're interested. So what do? Well, again, even if you don't have a particularly strong background in these areas, you draw a histogram, you see what the numbers look like, you look what the mean is, what the median, standard deviation, and then you start to get an idea what these numbers look like. And then there is another part to the story, which is already more, based on more advanced. There is some library, so to speak, of standard distributions that we know appear in lots of phenomena. And then you can look back at the numbers that you got and say, what I see here is something that looks pretty much like a normal distribution. Let me try and match the data that I have to such a distribution. That will teach me about the phenomenon at which I'm looking. So I'm suggesting something which conceptually is very much along similar lines. So let's see how. So to begin with, we have a very large graph. So it could come from cooking. It could come from brain research. I will say a little bit more about some examples from biology, something that I know perhaps a bit more about. Could be social networks, really tons of different sources. And we have to understand, we have to make sense out of this big graph. So I'm suggesting an approach that follows, in principle, quite similar lines. So there is a question to study, about which I'm going to say quite a bit during this lecture. So when we said, let's look at average, the mean, or median, or standard deviation, and so on, the question is, what parameters of this big graph do we want to look at? And I will have quite a bit to say about this. In fact, that's a main part of what I'm going to tell you. Then the next thing should be that we need a battery, or a library, if you want, of generative models of graphs. And then we try to match it. We discovered that the graph that we have at hand is something that could possibly be coming from a specific source. And then we try to match it and eventually learn back about the phenomenon that we are studying. So this is, in very, very broad terms, the scheme about which I'm talking about. Okay, so let me try and focus on the specific questions. We have the trouble is, or the source of the difficulty, it's also the source of the joy, because we're able to finally generate such graphs. So we have a very large graph. Sometimes, just to stress the point, it is often the case that the graphs are so big that there is no way we can store them in the computer. Sometimes they're not even directly accessible to us. So the graph exists somehow, in the universe that we're investigating. But if you want to know if two specific vertices, there is an edge between them, perhaps you have to do some measurement or some experiment or something like this. So graphs can be huge and not necessarily very easily accessible. These are the main points to keep in mind. So this is perhaps the main message of this whole lecture. So what should we be looking at? So what I'm suggesting, and as I say, I don't even try to imply that this is the final answer to the question, far from it. But all I am implying that this is at this stage of our knowledge, this is a good approach. It's scientifically extremely interesting, and I try to convince you that this is really very beneficial. So what is it? We have this huge graph. We sample a small chunk of it. We're looking at k vertices at a time. We have k vertices. We look at the subgraphs that they induce. And this is the substitute to these very basic parameters that we are looking at in the statistical distribution. We're looking at these, and they should tell us something interesting and worthwhile eventually about the phenomenon that we are studying. So this induces a distribution. When you have such a huge graph and you're looking at k vertices at a time, and you're looking at the distribution on these small subgraphs, this distribution I call the k profile of G. K is how many vertices at a time you're looking at. Okay, so this is, so just that we make sure that we're on the same page, or on the same slide. These are some examples of small graphs. They have vertices, these red dots. There are edges. An edge connects two vertices. And these are our friends for today. Okay. So just to illustrate that this is not a dreamt up thing, this is quite a good illustration. It's become an important subfield of, for example, biology. Biology is really a very good example of a field, where it's completely revolutionized by the fact that technologies for generating data have, expanded immensely, but this creates a problem in return, that now much of this data comes in the form of graphs. I'll illustrate in a second. And people are wondering, what should we do? So it's not that I'm making up this question. Many people are wondering about this. And my claim is at the moment we still don't have good answers to this. So you could ask, what's in these books? So one thing on which there is progress, which is helpful, but I think, from my perspective, not a profound enough progress, is in visualizing how to look at graphs. And that's already quite useful. People find it very useful. People are much better at looking at things and understanding. So this is a very typical thing. So you have some molecules like proteins or whatever. There is an interaction networks, proteins. Protein-protein interaction graph is one very good example of large graph that we are really interested in, that encodes a lot of important biological information. So you have this huge graph. You look at this, and it really looks, they called it a hairball. Good name. And then they have methods to zoom in and look at interesting parts of it and so on. Here you can already start seeing things. So visualizing big graphs is certainly a worthwhile thing to do, but one of my main claims is that this is far from being enough. We need much more than that. Or, for example, it could look something like this. Again, you start with some hairball like this, you zoom in, and then eventually you get to the level of individual proteins, and how they interact, and so on and so forth. So that's very good, but this is, as I say, it doesn't satisfy our needs. Okay, so now I want to come down to concrete mathematical or computational problems that we want to address. I just want to make it very clear that we have quite a bit of relevant mathematics, but these questions are far from being solved just in the mathematical sense of the word, and there are wonderful challenges here. So this is somehow, I'm sending perhaps a self-contradictory message here, but that's my message. What can I do? That on the one hand, there is a lot of wonderful and powerful mathematics that's relevant and can be used, but at the same time, there is still a very long way to go just on the mathematical side of things in order to develop the necessary background in order to stand up to the challenges that I mentioned. So here is one set of problems, what I call local graph theory. So remember, the K profile, you have a huge graph. Let me recall this basic notion. You have a huge graph. K is some integer, think 10. Something like this is good. And so the K profile, the 10 profile of a graph, you're looking at 10 vertices at a time. You're looking what is the 10 vertex graph that you're holding in your hand. That's a distribution on 10 vertices. That's the 10 profile of this big graph. What is possible? I'm giving you a distribution, some distribution. This appears with 0.01, this appears with 0.003, and so on. I give you a probability distribution on 10 vertex graph. Is this realizable? Is there a big graph for which this is the distribution? And as I'll explain to you, we are far from understanding even this very basic question. So this is a major challenge for the more mathematically inclined, and this is a fantastic set of problems which I'll try to explain later on. And then another set of problems on which we know even less and is perhaps even more exciting is what in the mathematical tradition of geometry we want to call a local to global theory. So suppose I'm telling you information about the K profile of a graph. What global conclusions can you draw? What large-scale properties of the graph does this tell you? And we will say, in fact, unfortunately about this, I will not even have time to say anything. So that's a fantastic subject, but we leave it outside the scope of this lecture. Okay, so one thing that I see people doing work with large networks, especially in biology, and as I said at the very beginning, my impression is that often they're not even aware of the existence of relevant theory, and that's one of my main goals, to explain that this theory exists, it's powerful, it's beautiful, and it should be used in order to address these problems. So I will explain, this is a part where the theoretical computer scientists in the audience can take a few minutes sleep, because by now that's completely standard, but I don't think that the other people are so aware of this, so I'll try to explain this the theory of the field of property testing. This is purely mathematics, and again, highly relevant. I'll speak about this, extremal and probabilistic graph theory. I will speak about a subject that's fairly recent, and explain how this connects to our subject, the notion of graph limits. I'm not sure I will even have time, but perhaps I will say a few words about this beautiful theory of flag algebras. And just to say that there is more. There is much more in the realm of graph theory that's very relevant to this, but things which I will not even have time to mention today. Okay, good. So let's start talking about property testing. So this is a subfield of theoretical computer science that has attracted a lot of interest in recent years. In fact, much of it started on this very campus, but developed all over the world. And let me explain this concept to you. So again, what's common to the whole setup is we have a huge graph, G. So just terminology. That's a graph, that's a set of vertices, and that's a set of edges. That's how we specify or describe a graph. And there is some graph property, which we call for the moment P. Don't worry if this looks a little bit abstract. I'll try to make it very concrete and clear. And our interest we're interested in answering the question, does this big graph G have this property P? So what could be, what are we talking about when we say about properties P? Here are just two examples. P could be the graph is planar. Planar means you can draw the graph in the plane in such a way that edges do not cross each other. Okay, that's a property of graph which has been studied a lot. That's a property of graph, just as an example. Is the graph 7 colorable? 7 colorable means that I can assign colors to the edges, red, blue, etc., under the condition that two edges, if they're connected by an edge, must receive different colors. Perhaps you have heard about four-color theorem and so on. Again, a very important concept and notion, both in combinatorics and in algorithm theory and theoretical computer science. So these are two typical things. So we could ask, here is a huge graph G, is it planar? Here is a huge graph G, is it 7 colorable? Okay? But as you'll see, we need to, the question as stated is too simplistic. We have to be more accurate about this, and I'll try to explain. The main thing, and that's critical with whatever you do with very big graphs, is that we simply are not, we cannot afford, in general, let me say this. In general, one of the most basic concepts of computer science, theoretical computer science in particular, is that computational complexity or time of computation somehow depends on how large the input is. And if the time is going to depend on how large the graph is, we lost the game before it started. Because these graphs are huge. So it's completely hopeless. So what we're looking for is an algorithm that takes a constant amount of time. We have an hour to dedicate to this problem. That's it, regardless of how large the graph is. Of course, you know, if you're limited with your budget, then you know that there are certain things that you cannot buy, right? In particular, here you have you're a beggar, so you can't be chooser. And there are certain things that you have to accept as derived from these restrictions that you require. So necessarily there must be probability in the game. You know, if you say I'm going to look at the first 17 vertices of the graph, perhaps there is nothing there. Perhaps nothing interesting is going on there. So you must use probability. That's a given. And as a result, you must accept the possibility that you're giving a wrong answer. And the other thing is, I mean, you wouldn't be surprised if we have a limited amount of time, the graph is so big, then it's just too coarse. We cannot really expect to be always correct, not just because of the probabilistic error, but just because we are not even looking at we're looking at a tiny part of the graph. So we need a notion of borderline cases. So let me be more concrete about this. So we want to decide whether a huge graph G has some property P. And what we want is this. If we're answering yes, then we want to be correct, period, with no cheating. Yes is yes. But no is not so well defined, or it's well defined, but you have to be taken with an appropriate grain of salt. So a graph, we're now dividing the word in this context to three parts. Normally you say the graph has the property or doesn't have the property. The graph is planar, it's possible to draw it in the plane, or it's not planar, it's impossible to draw it. Here, as I said, we're beggars in some sense. You know, we're restricted ourselves in a very strong way, so we have to give up somewhere. So we divide the word into three parts. One part is very simple, the yes instances. The situation that the graph is planar, it can be drawn in the plane. That's one simple case. Perhaps the graph cannot be drawn in the plane, but just barely so. You know, you remove a few, of course, if you remove edges, it becomes easier to draw in the plane. So you remove just a few edges and it becomes possible to draw it in the plane. So these are considered for us borderline cases. So we just want to distinguish between the yes situation and the really, in a very strong sense, no, but far from no and far from yes. So the answer is, we want to give a negative answer in the situation where the graph is far from having the property. In other words, let's say you have to change at least 1%. Let's say in the case of planar, you have to throw away at least 1% of the edges in order to make it planar. Now, if there is a graph that's not planar, but it's enough to throw 1 in 1,000 of the edges, then it's okay. We are willing, we accept the possibility that on such graphs we will err. So again, this is a key point, so let me repeat it. We have given up on the simple thing, here is a decision problem, say yes or no and be right, in two ways. One is it's probabilistic, we allow a probability of error, and secondly, the no, we only want to say to be correct with the no in a very clear way when we are far from having the property. So this is the basic concept. So let us, okay. So what does the algorithm do? You sample a set of vertices of constant size, and you look at the graph, and the decision just is based on this. That's it. There's nothing else that you can do. And we hope to have a good probability of success, at least, let's say, 3/4. So let's take a specific example. And the example is the graph property that I'm talking about is bipartite. So let me that's a bipartite graph. Perhaps it's quicker to just look at the picture. That's a bipartite graph. It's a graph whose vertices come in two parts, and all the edges go between a vertex here and a vertex there. So that's bipartite. So I give you a graph. If I draw it like this, the way it's on the screen a minute ago, it's very easy, but you don't see it like this. The graph is just out there. You can, you want to look at vertices, edges, be my guest. But the question is a graph bipartite or not? And that's it. So you want to make this decision. So what do we do? So as I said, there is really just a very natural thing to do. We randomly sample, let's say, a set of 1,000 vertices in G, and we check, is the graph that we got on the 1,000 vertices, is it bipartite or not? And that's something that we can do easily. That's something that students in computer science learn how to do. It's really a very simple thing. If the answer is not bipartite, then we answer the small graph that we hold in our hands is not bipartite, we say no. And then we are 100% sure, because the subgraph of a bipartite graph is bipartite. And if if what we see is bipartite, we say, well, we believe that the big graph is either bipartite, then we say the graph is bipartite. That's our answer. And it turns out, and that's quite a non-trivial theorem, which I'm not going to prove to you, that you are right with probability at least 3/4. So the scheme is very simple, and the scheme is very appropriate for the kind of problems we are talking about. So this is a highly non-trivial mathematical theorem, which I just state, I don't prove. And so just to make sure that we understand it, so let me repeat it. If a graph is 1% far from being bipartite, then with probability at least 3/4, if you look at a random set of 1,000 vertices, you will see it. Okay? So that's a very typical kind of theorem that we use in this area. So this is a kind of mathematics that's relevant, for example, for the study of very big graphs. And I'm skipping here, there is a famous saying that, any mathematical formula, you lose half of your audience. So I try to avoid this. And I'm sure I know many people in the audience here understand that there should be some epsilon and delta stuff in order to make this thing work, but we don't go into such things today. Okay. So again, let me just try and repeat this thing, because I know it's not very easy to understand in a first hearing. So we have two graphs, B and F. B for bipartite, F from far from being bipartite. And what we just saw is this. For each one of them, we're looking at the 1,000 profile. We're looking at the distribution of subgraphs with 1,000 vertices. One from B, the bipartite, and one from F, the far from bipartite. And the theorem that I just quoted says that these two distributions are very different from each other. So if you want, here is an example of something of the local to global phenomenon. You want to know the global property of being bipartite? The 1,000 profiles tells you that. Okay, good. So the global property is being reflected locally. The easy part is that every subgraph of a bipartite graph is bipartite as well. So if you see in your hand a non-bipartite graph, you know that the big graph is not bipartite. And the main content of this, it's a non-trivial mathematical theorem. If a graph is at least 1% far from being bipartite, then at least a quarter of the 1,000 vertex subgraphs are bipartite. Okay. Okay. And let me just tell you very quickly that this is one part of a really highly developed theory, and we understand precisely due to work of Noga Alon and Asaf Shapira exactly which properties can be tested this way, but we just, and that's related again to those who know, to semi-read regularity, and in particular, one thing, if you want to connect it to practical thing, many of these theorems at this stage are not suited for practical problems because the dependency on this 1% and 1,000 and so on, the 3/4 and so on, the quantitative aspects of this still leave a lot to be desired. Okay. Now I want to speak a little bit about one of my most favorite areas of math, extremal and probabilistic graph theory, which is again very relevant to what we do here. So this is a crash course on extremal graph theory or local graph theory. So you have a big graph, and it's a very intuitive and appealing thought that if there are many edges, if the graph is dense, then it must contain small, dense graphs. And the first example is more than 100 years ago, Mantel. And it says that a graph that has density more than a half, so if more than a half of the pairs of vertices have an edge between them, it must contain a triangle. And this is the best possible statement of this form. And this was further developed and became, so this person is Paul Turan, and he in the early 40s started to develop this theory, and his main theorem, mainstay of modern graph theory, a graph with density bigger than r-2 over r-1 must contain a complete graph on r vertices. If you plug here 3, then you get 1 over 2, so that's the 1/2 that we had before. And again, the bound is tight. And we understand more generally, I show you a graph H, and I ask how dense can a graph be without having a copy of H. We understand it, and this is the answer. Again, the same answer, the same form of an answer as in Turan's theorem. But now what is R? R is the chromatic number of H, the least number of colors that are needed in order to color H properly. Two vertices of the same color are not, there is no edge between them. And we understand a little bit also cases where this is good unless the graph is bipartite just to connect things together, but there are cases there that we know how to handle as well. So, okay. This is a huge graph, a huge area of mathematics, very highly developed. And as I'll hope to indicate to you, it's very relevant to the kind of questions that we are talking about. So let's return to our basic question of how to read a big graph. So let me return to this analogy with statistics that I drew at the beginning. So we need, what we're looking for, we have an empirical distribution. We're looking at the thing in our hands, which is just to look at small graphs. And we now need something which is a graph theoretic analog to this library of standard probabilistic or statistical distributions against which we can compare what we have in our hands. So you've seen such things, it could be normal, log normal, Cauchy. There are standard distributions like this. And the question is, what is the analog of this in the world of graphs? And this is a much, much less developed part. Again, an area on which too little has been done so far and really waits to be developed. So what we need is generative models of graphs. So how could a big graphs be generated? And I'll have something to say about this. Then we seek the best fit among these models to the graph that we have in hand, and then we read back the parameters. So it's quite a good analogy with what we do with statistical data. And then we are allowed to draw conclusions about the thing that the system from which, or the phenomenon from which these graphs came. So let me speak about generative models of graphs, how to generate large graphs. So there is one highly developed theory that's been around for 50 years. It had a really huge impact in many areas of mathematics, and this is the Erdos-Renyi GNP model. So Erdos and Renyi. We will meet him again later on. Well, I can say for myself, he was certainly a key figure for any combinatorialist. My generation, I met him first at age 16, and this made a fantastic impression on me. So to some extent, that meeting is why I'm standing here today. But let's proceed with this. So let me explain this model. So this is a model, a generative model of graphs, GNP. So n is an integer, and p is a number between 0 and 1. So you start with n vertices, and think of n as being large, because we really want to think about large graphs. And p is a probability, is a parameter between 0 and 1. What do? We start with n vertices. Independently, for each pair of vertices, we put an edge between them with probability p. Okay? I see I forgot to say with probability p. So, oops. So with probability p, we connect every two. So that's the role of p. It's a really very, very simple. The beauty of it is it's so simple. As a result, it's of course inappropriate. It's just too simplistic in order to describe anything realistic. But at the same time, this is the generative model that you understand the best. And by looking at it, I mean, the conceptual effect that this model had on how people understand big graphs is hard to exaggerate. It really had a huge impact. Per se, as a model of representing graphs that you see in real life, it's just too simplistic. Okay. There are other models of random graphs, of generating random graphs, which I will only mention briefly. For example, deregular graphs. You may want to have a large graph in which every vertex has the same number, let's say 17 neighbors. GNP is just not expressive enough, and this was solved around 1980. The key figure there was Bela Bolobash. So we know how to do this. I will not tell you how, but we know how to do this. There is more. There is models of random graphs that come from statistical mechanics, percolation. What do we do here? We start with a d-dimensional grid, and we maintain part of the edges independently with probability p. So again, this is just to indicate that we do have generative models of random graphs, but the situation is still very unsatisfactory. We don't have, there is something that I studied a lot, random covers or random lifts. So let me say that all the artistic part of this talk, whether you like it or you don't like it, so you should go to my wife, to Michal. And I kept telling her, there can't be a talk these days without a cat. So, and the reason there is a cat here is that this is one of my pet models. So that's the appropriate place to put it. So there is more. There is a preferential attachment, very interesting model in which vertices come in one by one. They connect themselves at random to existing vertices with preference to vertices of high degree. I don't want to even, there is other models of growing graphs where there are mutations which are motivated by biology. So let me just sum up at the moment and say our library of standard generative models of graphs is still way, way too poor. And this is a major challenge, and perhaps not so difficult to come up with new, interesting models. So it's a gold rush. So the younger scientists or budding scientists here, it's a situation where you can come up with a clever definition and do a few things and have your name remembered for many years. Think about it. Okay. I still want to give you more impression about how much we know in local graph theory, and just some beautiful pieces from graph theory, Ramsey's theorem. Ramsey's theorem, so perhaps this time it's a little easy to have lost our line. So we're still asking, what can a big graph look like locally? This is the theme. And one of the main theorems in this area, which is from the 1920s by Ramsey, says in simple words that total chaos is impossible. In a large graph, there must be some order. And specifically, it's a very important principle which comes up in a lot of areas of mathematics. In particular, if you have a large graph, then there must be a substantially large homogeneous set. So a clique, a set of vertices in which every two are adjacent, there is an edge between them, or the opposite, an anti-clique, a set of vertices with no edges between them. So let me... perhaps you heard this famous riddle. If you never saw this, then this is a good challenge for yourself and for your friends. If you have a party of 6 people, then there must be at least 3 who mutually know each other, or 3 who mutually do not know each other. And the number 6 is tight. It doesn't need to be so for a party of 5. So you want to know what happens if you replace this 3 by 4. Then this 6 is replaced by 18, and again, the number is tight. So just to, you see, that's the reason, think of it, here is a party of 5 people. So solid lines mean know each other, broken line means do not know each other, and you see there is no 3 here that know each other mutually, and there is no 3 that do not know each other. This is why the statement is true for 6. This is why it's not true for 5, this picture shows. And on the other hand, I don't know if you want to go to this party, but just in case, who knows. But you see, so for example, here there is a blue triangle. There is no red triangle. And this beauty, it's really a beauty. I don't want, I'm just, this is a graph with 17 vertices. I don't expect you to be able to check it online. There is no 4 clique and no 4 anti-clique. So this is the example that shows that what I said about 17 and 18 is indeed is tight, not just correct, but is tight. And as usual, we always want to understand these things for large graphs. So what is it? So this is the asymptotic version of Ramsey's theory, Ramsey's theorem. If you have an n-vertex graph, then necessarily there is either a clique or an anti-clique of size at least a half log n. And on the other hand, there are n-vertex graphs in which no set of 2 log n vertices is a clique and no set of 2 log n is an anti-clique. In fact, if you're looking at this G and P, where P is 1/2, then such graphs have this property. And in fact, you could say that with this discovery, which was, again, I should mention his name, made by Erdos, you could say that the probabilistic method was born with this theorem. So again, as I said, we're discussing asymptotic theory. And now what I want, so I see I will have to skip some of the things that I wanted to. So I want to tell you very briefly about a beautiful theory that has been developing in the last 10 or 12 years, which speaks about how to understand the theory of graph limits. And one of the first things when you do math analysis or calculus or whatever is the notion of a limit. So we're thinking about very big graphs. Very big graphs, we might as well think that n is tending to infinity. There is a notion of a limit. We know limits of a series of integers or sequences of integers. Is there a notion similar to that for graphs? And let me only say, I'll be a bit brief here, that all we need is a notion of similarity or a metric on graphs. And once you have this notion of similarity, you can say you understand what it means for a series to converge. A series converges if when you go far enough in the sequence, every 2 items there are sufficiently close. This goes under the name of a Cauchy sequence, if you remember, if you ever saw this. Not so important. So we need a notion of how to measure the similarity, a metric, how to measure a similarity among graphs. And there is such a notion. I'm going to skip it due to my time limitations, which is very interesting. Again, it's connected to this Semeredy regularity lemma. And these two guys, Latsi-Lovas and Balash-Segedi, only mathematicians are allowed to answer the next question. Where is this picture taken? Oberwolfach, very good. This is one of our meccas. You know, if the Simons Institute succeeds, then that's a good model. Yeah, this is one of the places that we do pilgrimage to. And they have a basic theorem in their theory. I mean, there are lots of other people, I must say, I'm not doing justice in terms of giving credit, but they are the two main figures in these developments, but there are lots of other wonderful people who are involved. And they say that the theorem says, it's a very beautiful theorem, that in the sense of metric that I mentioned before, a sequence of graph converges if and only if the local profiles tend to a limit. So this is a very profound theorem. It really tells you want to understand very big graphs. This is really perhaps, you know, if I'm trying to make a point, why this business that I'm preaching on, you know, understand the local profile and you'll understand the big graph. This is a major theorem that really justifies this claim. So the local profiles actually tell you if there is a limit to the local profiles, that there is a limit in the sense that I spoke about before. Let me spend just a few last minutes on some stuff in which I've been involved, but just really to give you a sense of, you know, these are the big questions. Great. Now, you know, what do we do on a day-to-day basis? Let's speak for a moment about three profiles. Just what can happen when you're looking at three vertex subgraphs? Just three. What could it be? So that's all. That's the whole repertoire. There are just four graphs on four distinct graphs on three vertices. That's it. And now I ask the same question. You know, what could be the three profile of a big graph? You would think that this should be, you know, an easy exercise. We don't know the answer. We don't know the answer. We know various things. I gave you two examples. P0 plus P3. So how often you see this plus how often you see this is at least a quarter. That's something that we know from the 60s. Recently, with these colleagues, we proved that, okay, at least one of these two numbers has to be small if you see this. Okay, so they can't both be very large. So we know various things like this, and some of them are quite non-trivial and interesting, but even this we don't know. And actually, so I promised that a return of Paul Erdos. So Paul Erdos, speaking about Ramsey's theorem. So remember, I told you that with triples, 6 vertices, you'll have a triple that's either complete or empty. 18 vertices, you'll have either 4 that is complete or 4 that is empty. For 5, you already don't know. And he used to say that if Martians land on planet Earth and say, either you tell us what this R55, that's the technical name for this, is, or we blow your planet. And he said the right thing to do is to get all the mathematicians and the computer scientists and the computers and everyone to work on the problem. Perhaps we can somehow save ourselves. But if they come to us and they say, either you tell us R66 or we blow the planet, the only sensible thing is to try to see if we can eliminate them. And it's a little bit the same with three profiles and 4 profiles. So 3 profiles we don't know, but my feeling is that, okay, it's something that we will get to see. 4 profiles is completely mysterious, and I just want to tell you this one thing, and I think that will be more or less the last story that I'm telling you. So let's return for a second to this inequality, which I said, the Goodman. Think about this for a moment. I mean, is this tight? Yes. Think of Gn1/2. What is the chance that I put every edge with probability a half? What is the chance of seeing? So it's a half times a half times a half. It's an 1/8. What is the chance that I don't see edges at all? Again, a half times a half there. So in Gn1/2, this is an 1/8, and this is an 1/8. So you got equality. So what would happen if we go up to 4 vertices? If you do the same thing, 4 vertices, there are 6 edges among them, so it's 1/2 to the 6, it's 1 in 64. So let's say the probability of seeing a full quadruple and an empty quadruple, in that case, is 1 in 64. And therefore, Erdos conjectured that there is such an inequality. But this is not true. As Andrew Thomason showed, this is not true. And the point is that we don't even have a good guess which graph attains the minimum here. So this is an indication that understanding the 4 profiles of large graphs is at the moment completely out of reach. So many of these fundamental things we don't understand at all. And let me just mention, because I have this photo here, so at least I should say one thing, and this would really be the last. There is a very important and powerful technique due to Sasha Razborov. Now you see him. Which he has become a key tool in all these areas. And let me only say in a very shallow manner what's the idea. So if you look at inequalities such as this P0 plus P3 is a quarter, these are linear inequalities. And Razborov generated a method to come up with quadratic inequalities. In particular, his method allows you to generate certain matrices from the local profile of a graph, and the theorem says that this matrix is positive semi-definite, and therefore you can use quite powerful machinery in order to make progress on many of these problems. And with this, I finish. Thank you. Please.
Well, you make some random measurements on a graph and want to guess how the graph was generated. It seems to me that there's a Bayesian aspect to this. You have to have some, prior probabilities that you.
No, I don't want. No. So let me be more accurate about this. Certainly, just again, I want to stress the point. We're far from having a good answer to this. But the methodology that I'm suggesting says this. We should have a list of generative models of graphs. We have, it's just too small. Let's expand it. Let's understand what the local profiles of these things are. Based on what you see in the big graph that you have at hand, already perhaps you eliminate most of these generative models. Remain 1 or 2 or 3. And then you ask yourself, okay, each of these models has some defining parameters. G and P, it's the P, and so on. And then you try and work back what these parameters are, and then you ask yourself, okay, what does it tell me about, the brain, the proteins, the social networks, what have you. This is more or less the concept that I'm suggesting. So if you want, what is my prior? My prior is that I'm limited in what I can understand, and therefore I have this library of generative models, and I refer to them. If none of them works, well, we have to start inventing something new. You run the...
Yes, you mentioned a few different generative processes like preferential attachment models and so forth. So given your statement about the mysteriousness of everything, I'm not hopeful, but is there any information about, given that the graph comes from this model, this distribution of K profiles would be different than if you just knew nothing about the graph?
Right. But these things, for example, take GNP, which admittedly is overly simplistic. In GNP, we understand exactly what the local profiles look like. So part of the theory that has to be developed, once we settle on which generative models are good for us, that I can imagine is not going to be too difficult a mathematical challenge to understand, to write out what the local profile of graphs that come from these different models. That I don't think is going to be such a major obstacle. That should be fairly easy, and then you have a reference line according to which to compare yourself.
So then the local profile could be a diagnostic about which model we should choose.
Right.
So you sort of talked a lot about the sort of Lovash, Szegedy sort of, dense world, and then there's this sort of whole other world that you sort of touched on with the deregular guys of the sort of Benjamini Schramm type stuff.
Right.
And, that seems to be sort of much harder, and so, in general, do you sort of have a feeling for, the graphs that are sort of out there in the real world? What's the relevant theory? Is it?
Yeah, so I think at this stage, I would think that if you're looking just at the connected profile where when you are, I wanted to skip it, but you're asking that perfectly, good question, of course. Then it seems to me that you do the same thing with just with the connected subgraphs, the connected K profile, and essentially the whole approach, I think, remains just as valid. Of course, the theoretical sides of this, as you correctly point out, is much more subtle and complicated, but the methodology, it seems to me, is still quite valid.
And there also, the generative models seem to be harder there as well.
Absolutely.
You don't have anything like GNP, right?
Absolutely. Yeah. The notions of limits are more sophisticated, no question.
I have a question that's a little bit less maybe theoretical and more practical. It's about trying to cluster graphs.
Uh-huh.
So if we have graphs that are generated by some noisy process, and we're measuring different types of associations between the same types of data, or maybe the same data in each graph, is there a way of actually using this K profile approach or something similar to, as a sampling process, to try to cluster graphs according to similarity when we've only sampled from some subset?
You could use the profile, the local profile, as a way to put things together as well. It gives you, we have, of course, lots of good metrics to compare constant length vectors. So, if two graphs differ substantially in their K profile, then probably you don't want to cluster them together. If they are very close, you may want to say, okay, perhaps they are somewhat related. So it suggests, I think, a very natural approach to your question. No. It's there is some fourth degree equation. That's the largest root, and then you do some more things to it. You throw some salt and pepper to it, and you do something. And it's not such a complicated thing, but it starts from an algebraic equation of fourth degree. It's
because we started with cooking, we ended with cooking.
quite appropriate.